Welcome to our paper Synthesizing Coherent Story with Auto-Regressive Latent Diffusion Models. I'm Xichen from New York University. This paper is a joint work with Pengda, Yuhong Li, and Huixue from Alibaba Group and Wenhu Chen from University of Waterloo. Today I'm going to introduce our motivation, task setting, our methods, qualitative and quantitative results, our adaptive methods, and limitations. Now let's start from the motivation. Our motivation is quite simple. Nowadays, there are many awesome text-to-image models like Imagen, SDXL, and DALL-E 3. When given a prompt like a red metallic cube is at the center, these models can easily generate images in high fidelity. However, when considering a story generation setting, for example, we want to add a new green rubber cube at the right of the red metallic cube, it is really challenging for existing text-to-image and text-to-story methods. Because they generate images independently, which means these methods do not condition on previously generated images, so the result still aligns well with the prompt. It is not consistent with the first image. Like the red metallic cube, the background, viewpoint, and lighting are all completely different. Well, if we can condition on the first image and auto-regressively generate the next one, it is possible to keep the consistency between these images. In summary, we would like to note that a picture is worth 1,000 words. We can not only use prompt to precisely describe the object's scene, style, and viewpoint lighting. In order to generate coherent stories, we need to preserve as many details across images as possible. While existing work assumes that images are conditional independent and do not generate images with reference to previous ones. To tackle this, we employ an autoregressive generation manner and estimate the posterior directly, which makes it possible to preserve the consistency between images. We mainly focus on two tasks: story continuation and story visualization. For story continuation, the model is given the first frame as a source frame and need to generate the other frames according to the captions. Well, in the story visualization setting, the model needs to generate all of the 5 frames from the given captions. Then I will introduce our detailed method. This is a brief illustration of our autoregressive generation process. First, we generate the frame 2 image using its caption and also the image caption pair of frame 1. Then we generate frame 3 image using its caption, the image caption pair of frame 1 and 2. By doing this, our model is able to encode history images for future image generation. Here is our detailed model architecture. We use click model for text encoding and blip model for multimodal encoding. We add tap embedding to denote the clip embedding and blip embedding. We also add tap embedding to denote the order of frames for blip features. Then we'll show our qualitative results. This is the character set of our Poro dataset. We have 9 main characters in this dataset. And this is a story visualization case without any given source frame. We need to generate all 5 frames from the captions. You can see that the character is consistent. We also preserve the consistency of the environments like in the last 2 frames. And this is the same case but in story continuation setting, which means this first frame is provided as a ground truth. We can also get a coherent visual story here. And this is another story visualization case on Pororo dataset. And the same case under story continuation setting with a given first frame. We can observe that the blocks is quite consistent. Here comes the character set for Flintstone dataset. We only do experiments under story continuation setting on this dataset. We have 7 main characters in this dataset. You can find the gel is very consistent across these 2 frames. The layout of the images are also quite consistent. And this is another case. We can also keep the consistency of the blue glasses. Apart from these 2 datasets, we also adopt visual storytelling dataset for real-world story continuation. And the style is quite consistent in these generated stories. And in this case, we start from a grayscale source frame. As you can see, our generated images are in grayscale and the house is also quite consistent. We also provide quantitative results here. We use FID score to evaluate our model's image fidelity. As you can see, our AR-LDM greatly outperforms previous state-of-the-art methods on 3 datasets under both story continuation and visualization setting. We also carried out large-scale human evaluation on 3 datasets. We randomly select 500 samples of each dataset to be evaluated for each criterion. We found that AR-LDM outperforms story-stelling by a large margin in consistency, relevance, and also visual quality. Beyond these results, we have also explored to adapt AR-LDM to new characters. Take the Flintstones dataset as an example. Is it possible to add 1 new character to the character set? We propose the adaptive AR-LDM to tackle this challenge by fine-tuning the model. We find that we can adapt our model to the new character while still able to correctly draw the existing character, such as Fred. While our method still have some limitations, such as in this case, AR-LDM cannot provide satisfactory results. This can be attributed to 2 problems. The first is due to the lack of mask image modeling laws. Blip cannot ground the entity correctly. As you can see in the 3rd frame, AR-LDM draws the quilt in the color of the clothes. What's more, since we are doing auto-regressive generation, so that we can only know that Fred is wearing a green shirt from the caption of the 4th frame, and it is impossible for us to draw it correctly in the first image. Thanks for your attention. For more results, you can scan the QR code below to get the paper and the code.